Okay, folks, let's get started. Can you hear me in the back? Okay. This is lecture number 26, Friday, April 3rd, announcements. There's a Gorilla section this weekend. If you want more practice with the Scheme language, your homework's in Scheme, your quiz next week is in Scheme, the next homework will be in Scheme, and the project's all about Scheme, so you might as well learn it now. If you got a feel for it but want some more practice, come to the Gorilla section, which will be on Sunday starting at noon in 271 Soda. Questions about that? It's the place to be. Homework 7 is due next Wednesday. There's a homework party on Tuesday. This homework has a lot of questions to it. Not only is it getting you familiar with Scheme, but it's also making sure that you are paying attention during that last unit before midterm 2 when we talked about set implementations. So you're going to have to go back and relearn how those set implementations work and then implement them in Scheme. Quiz 3 will be released on Tuesday sometime, and it will be due on Thursday. Quiz you have to do on your own. In the meantime, you should be working on composition revisions for projects 1, 2, and 3. I know there's a few quirky issues with the submission system. We're trying hard to work those out. How many people tried to submit but couldn't? Not too bad. I think I'm back. Now is an excellent time in the course to check and make sure that your stuff is being graded correctly. So there's a pass, no pass deadline today. We tried to get all the grades in there so you could see what was going on. Please take a second look. What? How about Monday? Is that what you wanted? You're indifferent? You just want internal consistency. That's good computer science thinking. Okay. If you notice something fishy with your grades, just follow the instructions here and you can ask for a regrade request. Hello. Oh, I like my wife too. Okay. Today is a very exciting time in the progression of this course. If you were at a different university on the quarter system, this course would be over, and you'd go on break or something like that. But since we have a whole semester, we get an extra unit at the end. And what we're going to do now is something that most introductory computer science courses don't bother to do. Most teach you how to use a programming language, but in this course, we'll teach you how to build your own programming language. And that's meant to empower you to build programming languages wherever you want, and also to make sure that you understand the mechanics of what's going on when an interpreter runs a program. We're going to go into the internals and take a look at that. So I find this stuff very exciting. Let me just tell you a little bit about programming languages. We've mostly been studying Python. Now we're working on a little bit of Scheme. We'll even learn one more before this course is over. But just picking one is not what you want to do in life, because a computer typically executes programs that were written in many different programming languages. That's the modern computing environment. And there are different classifications of languages. So there's something called a machine language. We haven't talked much about that. It's mostly what you talk about in 61C. In a machine language, the statements in the language get interpreted by the physical hardware of the machine itself. So there's a fixed set of instructions in these languages, and each one has an implementation in the circuitry of the chip that runs the computation, the central processing unit of your computer. But these languages tend to be very limiting. So the operations refer to specific hardware memory addresses. There's no method for abstraction whatsoever. You can't use names, you can't define procedures. That all has to be something that you live without if you're writing in a machine language. And then there are high-level languages, and Python is one of those. Almost all programmers spend their time writing high-level language code. And these statements and expressions are interpreted by another program. We have to write a program that gives meaning to these other high-level programming languages. And we write them originally in terms of machine languages, but then one language can help us implement an interpreter for another language. So this idea is very profound, actually, that the interpreter for a programming language is actually just another program for almost all languages that anyone actually uses. The nice thing about high-level languages is that they can provide us with means of abstraction. We can give names to things, we can define functions, we can use objects. All of these are properties that somehow got implemented by some program that knows how to interpret these languages. Questions so far? A machine language does not require an operating system. An operating system is typically written in a high-level language. Really all you need is hardware, some chip that knows how to execute those instructions. Right, so there's a lineage of languages, both in terms of the ideas about why the language is designed the way it is, and also in terms of the implementations of the interpreters or compilers. So the first implementation of the Python interpreter was written in the C language. The first implementation of Lisp was written in Lisp, actually, but it didn't run because it was on a chalkboard. So then they copied it into Fortran, and then it ran. Yeah, so that's right. So the question is, does every CPU have a different machine language? Well, not every individual one. One manufacturer will stick to a particular specification. But different CPU manufacturers have, over time, chosen different instruction sets for their chips. And it's up to high-level languages to make sure that your code can run on lots of different manufactured chips. So in the beginning, you design a circuit which processes instructions one by one, and that's a machine language. So the implementation of some language is actually just in hardware. That's where it all begins. And then you can build software layers on top of that. And there are typically many levels. Interesting questions. One of the goals of a high-level language is to abstract away system details that may vary from computer to computer. So we release software for this course. You build your projects. You might be building them on different machines made by different manufacturers. And in fact, the exact set of instructions that are run on those machines may differ. But the high-level language interpreter is meant to run on lots of different platforms. This makes our lives much easier as programmers. You can actually see some of this at work. If you write some Python code, here's a definition of the square function. You can see that what happens is it gets compiled into an entirely different language called Python 3 bytecode. And Python 3 bytecode is a set of instructions that doesn't include the vast richness of Python, where you've got all these, what have we done? List comprehensions and higher order functions and all that kind of stuff. Instead, it has a very limited instruction set that basically just says, I'm allowed to load in certain values for certain names, which have to be at particular positions, and then I have built-in ideas like binary multiplication, multiplying two numbers together. And if you want to see this, you can import the dis function from the dis module, and then disassemble any function to see its bytecode. So you can inspect exactly what's running. Now this bytecode actually isn't exactly a machine language. It's one level higher than that. There's something called a virtual machine that intermediates between the Python bytecode and the actual chip that runs it. Topic for another class. My only point here is that you can see that different languages are at work in every program that you write. Now, inventing languages is not something we should be afraid of. Instead, it's something we should embrace. It's a powerful form of abstraction to say, if I want to talk about this kind of problem, I should use this vocabulary, these structures. And we do this in, science and mathematics all the time. We invent vocabularies, we invent languages in order to describe what's going on. And here, we can do the same thing. We can invent a new language that's tailored to a particular application or problem domain. And so what do I mean by particular type of application? Well, there's a language called Erlang, and Erlang is designed to handle concurrent processes effectively. So it's built into the language that you can express how to handle multiple different things happening at the same time and resolve them so that the behavior is consistent even if one thing happens before another. And so this language was designed for a particular type of application, and since it works well, it's used for things like, people using ATMs all over the world, and somehow they have to have a consistent bank account, or people are using chat servers and many simultaneous connections all over the world, and everyone needs to have the right conversation. So that's a type of application that motivated a particular kind of programming language. Sometimes the domain of what you're going to use the language for dictates what kind of language you use. So one of my favorite examples is the MediaWiki markup language is the language that people write Wikipedia pages in. And it's a language that mostly just looks like regular text, except for that you can format the text, you can add bulleted lists, but you can also link to other pages. And that's really important for Wikipedia, where you have all these different links between articles. And that's a programming language too. It's not expressive like Python, and then we can't write, actually, I'll take that back. In this language, you can perform lots of computation as well, because sometimes a lot of computation is required in order to lay out all the contents of a Wikipedia page. And some group of people just invented this language. Okay, so what is a programming language? Well, it's something that has a syntax, which is a description of the legal statements and expressions in the language. You have to have a closing parenthesis for every opening parenthesis, etc. And it has a semantics. And the semantics, or meaning, is the set of execution or evaluation rules for all of the statements and expressions in the language. So we've been, since the beginning of this course, going through statement after statement. We did if, and then we did while, eventually we did for, we did the class statement, and for each one of those, I showed you the structure, that's the syntax, and then I gave you an execution rule, that's the semantics, and those two things together define the language. Now, languages can be defined in two ways. You either write down a specification of how it's supposed to work, and this is supposed to precisely describe the syntax and semantics of the language, or you just build an interpreter. People have built languages in both of these ways, and either one can be quite successful. Python started out because somebody built an interpreter, but now there's more and more specification behind it. Lisp, well, Scheme in particular, is coordinated mostly by a specification, and there are lots of different implementations that are all supposed to behave the same way. Now, in reality, they don't all behave the same way, and that's kind of annoying. Okay, questions? Okay. So now we're going to go through the parts of what it means to build an interpreter. And there are many parts. Basically, you have 2 weeks to learn this. You don't have to learn it all in the next 35 minutes, but I'm going to give you a sketch of how an interpreter works from top to bottom. And this sketch is actually fully released to you. It's part of the course textbook. It's called the Scheme Syntax Calculator. And it's a programming language that just performs elementary calculations, adding, multiplying, subtracting, even dividing. But I just wanted to give you all the source code. You should spend some time studying it on your own. And then when you build Project 4, that's like a really big extension of this core idea. Okay, so one part of it is parsing. The program begins its life as just text, and we somehow need to figure out what structures are there to interpret. So a scheme list, in particular, is written as elements in parentheses. So you put an open parenthesis, and then you write more expressions, and then you close the parenthesis. And each element can also be a combination, another scheme list, or it could just be a primitive, like a number 2. So when you have some complicated scheme expression that looks like this is really one combination which has a plus in it first, followed by another combination, and another one here. The task of parsing a language involves taking the string, which is just parenthesis plus parenthesis times space 3 space parenthesis plus space, and turn it into an expression representation that allows us to perform interpretation. And the goal of the parser, so reading and parsing are the same things, and the parser is the program that does this, is that it has to check and make sure this expression is well formed. Is there really a closing parenthesis for every opening parenthesis? Is every number really a number? Stuff like that. Okay. So here's just a glance at how it works. This is a program. So this is the textbook composingprograms.com. There's this example. One of the files in this example is called schemereader.py. I'm going to show you what it does. Schemereader.py doesn't interpret anything. All it does is read in an expression in Scheme and then print it out again. So here's an expression, 3. And what I'm going to show you is what it looks like in Scheme and also an underlying Python representation of the same thing. So 3 is represented as 3 in both languages. But if I create a list, 1, 2, that's a valid Scheme expression that in Scheme I would write like this. But as I've been saying over and over again since Monday, this is really just a linked list. A linked list where the first element is 1, and the rest of the list is a list containing 2. So the same thing as that. So the underlying representation for this scheme list 1, 2 is going to be this linked list structure. And for this linked list that has only one element, it will be this structure, where nil represents the empty list. So these are two different equivalent things, one written in Scheme and one written in Python, that are both representations of whatever I typed in. Now, how did I do that? How did I get this pair 1, pair 2 business? Well, here's a little sketch, and then we'll go through in detail. Go away. So first of all, what's a pair? A pair is like a link. There's a class pair. We'll go through the details, but right now I'll just show you how it works. A pair can be used to construct something that looks like a linked list, and when you just look at it, its rep string looks exactly as if it was constructed, where nil represents the empty list. But when you print it out, what you see is the Scheme representation. We can compute the length, which is how many elements are in it, 1 and 2. You can index into it. And then there's also a method called map, which takes in a function and applies that function to every element, giving me back a linked list made out of pairs, where in this case we've added 4 to each one. So 1 plus 4 is 5, and 2 plus 4 is 6. Okay, so we have a pair which is the same as a link, except for it has some fancy printing properties. When I print it out, it looks like a scheme list. Okay? Question? No question. Okay, so pair exists. Now you know that it always has two things in it. And then what I'm doing here is every time someone types something in, I'm calling a function called schemeRead. As part of your project, you will extend this function, and that's my way of getting you to understand how it works. schemeRead takes in some text, like an open parenthesis and a plus and a 1, and then another open parenthesis and a plus and a 2, 3, and a 4. So this is like as if I had typed in +1, and then I went to another line, and then I typed in 23 and 4, and then I closed those parentheses. And maybe I put that there too. Oh, got too big. Okay, let's look at it for a second. So it reads in the first full expression from the line, which doesn't include that because the expression ended here. And it gives me both the scheme version and the nested version, which says this is a linked list that starts with a plus, followed by a 1, followed by the third element is a linked list itself. The schemeRead function is a tree recursive function that does the following. It looks for open parentheses. Whenever it finds an open parenthesis, it calls read tail, which reads everything up until the matching closing parenthesis. I'm not going to go through the code now, but I will later in the lecture. Read tail gets called on the rest of the text and looks for that closing parenthesis, at which point it's done. Okay, I'll go through the details in a minute. But the point is, one piece of a programming language is to implement this procedure that takes in a bunch of text and turns it into nested pairs. Remember that every scheme list is a first element and then the rest of the list. Okay. Let me try to give you some more details in pictures instead of in code. Hopefully these pictures will help you understand the code when you read it later. Okay, a parser takes in some text and returns an expression. An expression is an instance of the pair class. So in comes the text, and we first perform lexical analysis. You don't have to figure out how to do this. We've done it for you in this class. That gives you tokens, and the tokens get fed into syntactic analysis, which gives us an expression. What am I talking about? Okay, so the text starts out like this. It's just, parentheses and pluses and numerals, 1s and 2s and decimal points and stuff like that. What lexical analysis does is it breaks those up into the individual pieces. A parenthesis is different than the plus, even though they happen to not have a space in between each other. It's a property of the language that these are separate things. The beginning of an expression and then the addition symbol. And it does this, for instance, recognizing that 1 is a number, that 2 and 3 are actually part of the same number, but that the closing parenthesis is a separate thing, even though they're all next to each other in the original text. So there's a little bit of work to just figure out how to break up the original text into tokens. It gets rid of spaces. That's its main job. And glues together numerals into whole numbers. So 2 and 3 together is not two separate numbers, but 23. And it even figures out that 5.6 is just one big number. Very impressive. Okay, so that's called lexical analysis. This is an iterative process. You go through character by character in the string, looking to make sure that everything is formed correctly, so you don't have things like 5.6, 0.7, 0.8, because that's not a number. And it determines whether something's a number or a parenthesis or a symbol like plus. And this can actually run one line at a time. It doesn't check for opening and closing parentheses matching up, because that's the job of syntactic analysis. Okay, so what does syntactic analysis do? Well, this takes in all three of these lines together and tries to build one big tree structure. The tree structure, that's really a linked list starting with a plus and followed by all of this other stuff. So instead of writing it out here, I'll write out the scheme version. The scheme version looks like this. So you might think, oh, I've just deleted all of the spaces. But there's more that's happened here. I've built an underlying representation of a linked list where the first thing is plus, the second thing is 1, and the third thing is a whole linked list expression that contains negative and 23. This requires the tree recursive process scheme read that we just looked at. It balances parentheses, it gives us back a tree structure, and it handles multiple lines. This will all make more sense when you actually work on it yourself, but you got to start with a grand tour of everything that you're going to see so that you have some reference points. Any questions? Okay, let those questions keep marinating, and let me just give you an idea of how the process works. You get in a bunch of text, and you want to figure out its tree structure. Well, you perform a syntactic analysis, and the one that we perform is called a recursive descent parser. So it looks for a parenthesis, and then it tries to find everything until the closing parenthesis. We're running short on time, but okay, we'll do this too. So the question is it hard to figure out the structure of a bunch of words? In Scheme, it's easy. For every opening parenthesis, there's a closing parenthesis. But there's kind of an analogy here with the English language. So the English language has structure too. Every sentence is built up of some subject and some predicate. And the question here, I guess, is, can you figure out, just by looking at the last few words, what's the structure of a sentence? And it turns out it can be hard in certain cases. So here's a classic example of a sentence that's kind of hard to read. The horse raced past the barn, fell. How many people think this is a correctly formed English sentence? Or just me? How many people think it's nonsense? Where did fell come from? Okay, so here's how you would interpret this sentence. You can race a horse, just like you can ride a horse. So as a synonym for race, think ridden. The horse ridden past the barn fell. So ridden, can I really say ridden? Well, yeah, I mean, in English you can say the horse that was ridden past the barn fell, or you can just leave out that was. Okay, so what happened here was it was really hard to interpret this sentence because there was another reasonable interpretation that raced was not introducing this relative clause, but instead was the predicate. But that's not really the case. This was the whole sentence subject, that horse that was ridden past the barn, and it fell over. Okay, so English is really hard to parse, is the only moral of this story, but Scheme is not so bad. So syntactic analysis of Scheme goes like this. You take in a bunch of text, and each call to Scheme read consumes an input token for exactly one sub-expression of the whole expression. There's base cases here, which are the symbols and numbers, and then there's recursive calls where you just call Scheme read on a sub-expression. Okay, so here's the whole thing. One call to Scheme read is going to consume the whole thing, but it's going to do it by consuming everything until it finds a matching closing parenthesis. So in the first call, it will notice an open parenthesis. It will then keep consuming whole expressions until it's left with nothing but a closing parenthesis. The first one is a base case, plus. The next one is a base case, plus. The third one involves consuming this entire sub-expression. So it goes to there, at which point it checks what's next, and what's next is not a closing parenthesis, so it's not done. And then it consumes this entire sub-expression until there, and then it checks what's next. What's next is a closing parenthesis, so it's finally finished. So let me just say the whole thing while I point to the code. Scheme read takes in a sequence of tokens. It pops off the first one. Nil is a base case. Everything else that's not one of the parentheses is also a base case, like a number or a symbol. Otherwise, open parenthesis is the recursive case. The recursive case takes the rest and just reads expressions until it finds a closed parenthesis. So it finds a closed parenthesis, then it's done. Otherwise, it reads another expression, that's the first one, and then it reads the rest of the expressions, and it returns a pair containing the first and the rest. And that bit of code actually walks through a list of tokens forming a tree structure. That's cool. Okay. The program that I showed you so far was called SchemeRead. And what does it do? Sorry. It takes in an expression and tells you what's the structure of that expression. So the structure of plus 1, 2 is just plus 1, 2, which is a linked list starting with plus followed by 1 followed by 2. If instead I sneak in a minus sign here, then I get this nested structure. Plus followed by 1 followed by a whole expression. Now that was called SchemeReader, but the Scalc program is even more powerful. It takes in the same kind of thing, plus 1, 2. It reads it into this structure that says add 1 and 2 together, and then it actually adds 1 and 2 together. Whoa. You can even add 1 and negative 2 and get negative 1. Or you can multiply 5 and 13 and 31 and get 2015. I woke some people up. Excellent. What, you don't think I came up with this on the fly? Mostly preparing for lecture is coming up with ways of making 2015. That is my life. Okay. Moving on. This calculator thing that we've built is non-trivial in the sense that we can span, multiple lines. We can nest however we want. This is not going to come up with 2015 because I didn't prepare enough. But the point is, it somehow takes this mess, parses it in order to get a tree structure, and then applies a certain procedure in order to actually figure out the value. So now what we want to do is look at the procedure that gets you from the tree-structured expression to the value itself. Okay, so the first thing we need is the pair class. We looked at that already. A pair class represents scheme, pairs, and lists. A list is just a bunch of nested pairs because all scheme lists are linked lists. A list is a pair whose second element is either a list or nil. Okay, so I showed you this briefly. There's a class called pair which takes a first and a second element and stores it. If I create a pair of 1 followed by 2, 3, and I print that out, I see the scheme list structure. So that's a property of the pair class that when you print it out, you see the scheme structure that underlies it. And the length of this is 3. If I build a pair of just 1 and 2, that's not a well-formed list, so you see that dot. This dot means that the element after the dot is the last element in the pair, the second element in the pair. So what happens if I construct a pair whose first element is 1 and its second element is a pair containing 2 and 3? Well, that corresponds to this dotted, malformed list expression. if you try to compute the length of a non-well-formed list, you'll get an error. So it doesn't have a length. So you can try to call length on it, but it will say malformed list. Excellent question. Oh, there it is. So what's the length of this thing? Length attempted on improper list. Well, that's a really good question. Okay. Now, the big insight here is that scheme expressions are really just scheme lists. The source code of this language is just data in the language, which makes it easier for us to write interpreters. Is there a question in the back? Error handling requires using exceptions, which we talked about on Wednesday. I'll show you a little bit in the code in a minute. Okay, so, right, I could do this. I could open up Scheme Reader and create some pairs for you and print them out, and you'll see that that works, just like I said. Oh, so why do they have the dot? Oh, I chose that. And I chose that because there is no length of an ill-formed list. That's all I got. Okay, so what's the calculator language? Well, the calculator is just a subset of scheme that only lets you add, multiply, subtract, and divide. The calculator language has primitive expressions and call expressions, nothing else. The primitive expressions look like numbers. The call expressions are combinations that start with either plus, minus, times, or divide, followed by 0 or more other expressions. So it does allow nesting, but it doesn't allow defining new functions or anything fancy like that. Expressions are represented as scheme lists, which are instances of the pair class in the underlying Python representation. So if I have an expression that looks like this, that corresponds conceptually to an expression tree, where I would add 4 and 5, I would multiply 6, 7, and 8, I would then multiply 3, and whatever that result is, and whatever that result is, and that's how I would get the result of the whole thing. And that expression tree is represented as a linked list, where this says first and second. Each one of these is a pair. This is a pair where the first element is times, and the second element is this whole structure. The structure that starts with 3 and is followed by an element for this sub-expression and followed by an element for this sub-expression. Box and pointer diagram. By the way, if you want to generate your own box and pointer diagrams, here's a link to some web app somebody made to draw box and pointer diagrams for you. Okay, what's the meaning of a calculator expression? That's the semantics. Well, the meaning is just the sum or the product or whatever that you get when you evaluate one of these. Well, we have to write it down as a procedure. The value of a calculator expression is defined recursively. A primitive evaluates to itself. A call expression evaluates to its argument values combined by an operator. So you have to first evaluate all the operands, and then you combine them with the operator. What does it mean to combine them? Well, if it's plus, you add them. If it's times, you multiply them. So plus is sum of the arguments, times is the product of the arguments. Minus has this funny rule, where if there's just one argument, you negate it. Other than that, you subtract the rest from the first. And divide, if it has one argument, then you invert it. So divide 3 gives you 1/3. Otherwise, if there's more than one, you divide the rest from the first. This is exactly how scheme works, and this is how the scheme calculator works too. Okay, so if I take this expression, 5 plus 7, 8 plus 6, 25, that corresponds to this expression tree. In order to evaluate it, I first have to evaluate 5 and plus 7, 8 and plus 6, 25. In order to evaluate plus 7, 8, I add 7 and 8 together, the sum of the arguments. In order to evaluate plus 6, 20, and 5, I sum the arguments there. and then I multiply 5, 15, and 31, 2015. Did I get it wrong? Oh, you're right. This is wrong. Let's fix it real time. Oh, no. This is important, people. All right, we're back in the game. Whew. That might be right or it might be wrong, but it's too late now. We're going to move on. Okay. So I've told you a recursive procedure that takes in an expression tree and actually just computes all of the values for all of the sub-expressions and then applies one of these procedures, either summing or producting or negating or inverting or subtracting or dividing. And that's the whole language. What does the code look like that does that? Well, it's not too different from what I just described. So there's a function called eval. Actually called scalc eval. So we know what kind of language we're evaluating. It computes the value of an expression. And the value is always a number. So it looks at the type of the expression, which is either a primitive like a number, or it's a combination that starts with plus, minus, times, or divide, and decides what to do. So it dispatches on the type of the thing that gets passed in. And here's the actual code. So the interpreter for the language, half of it is on the screen already. What it says is, an expression comes in. If that expression is just an integer or a float, then its value is the expression. Otherwise, if it's a pair, we assume it's a linked list, so we assume it's well-formed. We get the rest of the linked list, that's exp.second. We call calceval on each element, collecting the results into a linked list. And then we call a function that I haven't showed you yet called calcapply, which applies the plus to all of the argument values. So remember, exp was an expression which might have had nested sub-expressions within it. But by the time I call calceval on every one of those nested sub-expressions, I'm just left with a bunch of numbers. So calcapply just has to figure out how to take an operator like plus and a bunch of numbers and add those together. So this says a number evaluates to itself and a call expression evaluates to its argument values combined by the operator exp.first. So like what's the difference between plus and times? Right, so that's in calcapply. We haven't gotten there yet. So that's the one hole in the story. Is how does calcapply work? I'll show you in a minute. Okay, but there is a recursive call here, and in fact it's tree recursive because we're calling calceval on every sub-expression except for the first one. And calcapply is the thing that actually knows how to add. Exp.first is limited to either being plus or minus or times or divide. And this is just numbers. Okay, so how do you actually add together a bunch of numbers? Well, here's an interlude. I'm going to teach you a Python higher order function that allows you to combine a whole list of numbers using just one binary operator. It's called reduce. Reduce takes in a reduce function, a sequence S, and an initial value, and it combines the elements of S pairwise using the reduce function, starting with initial. What? Well, for example, if I want to multiply 2 and 4 and 8 together starting with 1, that's equivalent to multiplying 1 and 2, multiplying that result by 4, multiplying that result by 8. And so if I reduce 2, 4, and 8, starting with 1, I get 64, which is the product of all these numbers. So taking the product is like reducing with multiply. Here's the implementation. You just say, I start out with the initial value, reduced is the thing I'm going to return, And then for every element in X, I call the reduce function, which was one of my arguments, on whatever I've reduced so far, and X, the next element in the sequence, and then I return reduced. So you can implement summing lots of numbers this way, or multiplying a bunch of numbers this way. Reduce fun is any two-argument function that can combine two things, and S is the sequence of values where you need to combine them all. So they each need to be the second argument of reduce fun at least once. And we start out with an initial value that's the first argument. Okay, so what happens if I reduce using POW, which raises one value to another, the sequence 1, 2, 3, 4? Well, 2 is my initial value, so I take POW of 2 and the first element of my sequence. So 2 to the first power is 2. Now I apply POW again to 2 and the next value in my sequence, which is 2 in this case. So 1, 2, 3, 4 is the same 1, 2, 3, 4 being built up here. 2 to the second power is 4. What about 4 to the third power? That's 64. And what about 64 to the fourth power? Well, that's big. Okay, so that's what it means to reduce a sequence of numbers together. And this is actually built into the language, or I've just defined it here for you in Python. I think it lives in the itertools module. Okay, so how do you apply built-in operators? How do you add? Here's how you add. The apply function just looks at what it's supposed to do and calls the appropriate reduce. So there's only plus, minus, times, and divide. What calc apply does is it says, is it plus? Well, then I'm going to add all the arguments together. Is it minus? Well, then I'll do the minus thing. If it's times, then I'll multiply all the arguments together, etc. So we sum the arguments, or we subtract all but the first from the first, etc. So let me just show you the code, and then I'll take your question, I promise. Okay, so what does plus 1, 2 actually do? I'm going to open up scalc.py, calceval, like I said, just calls calcapply, and calcapply says if it's a plus, reduce using add. If it's a minus, make sure there's at least one argument. If there's only one argument, len args equals 1, then negate it. Otherwise, subtract, starting with the first value, all of the elements in the rest. And there's multiply and divide. So really, we're letting Python do the arithmetic. It's not like we have to define what it means to add numbers together. And this is true in every interpreter, that the underlying chip knows how to add together numbers. It's only up to us to figure out how to interpret the semantics and the syntax of a new language. Now notice all these type errors and stuff. Well, a big part of defining a language is making sure that you give feedback to the user when they've done something wrong. So what happens if I just type 1? It says 1 is not a symbol. I don't know how to 1. I only know how to add. And why did it do that? It's because right here, why did it do that? Oh, because right here, it checks to make sure that the operator is a symbol, and if it's not, then it complains. What about an unknown operator, like question mark 1, 2? Well, it says question mark is an unknown operator, and it says that because I raised the type error right here. Or what about these errors? Like here it says subtract requires at least one argument. So if I try to subtract nothing at all, then it will say minus requires at least one argument. And the same is true of divide. So notice that I've raised all of these errors, but I'm still able to keep going in my program. That's because the whole program, where this is the start when I run this application, goes forever while true, tries to evaluate the next expression, and if there's an error, then it just prints it out and goes right back up to the top of the try statement. So here we're using exception handling to make sure that the whole Python program doesn't crash. Instead, I get a second try, to get my scalc expression right. And it's printed out the error that went wrong along the way. Okay, so go download this program, read all the source code, post questions on Piazza. If you understand this, then Project 4 is much easier.